quantum machine learning algorithms for knowledge graphs. So please go ahead.
Okay, yeah, thanks for inviting me, us, to give this talk. So I will start, and then Yunpu will take over. And yeah, we are both with the University of Munich and Siemens. So I'm not sure everybody's familiar with the concept of a knowledge graph. So I want to motivate it by the idea of a universal world description at the human abstraction level. I think somebody has its microphone still on. Some noise on the audio. So here, so the world consists of constants, things, and entities like Jack and Mary, and predicates which specify the relations between things like likes and looks at. And if you then compose an SPO triple, you have basic statements like Jack likes Mary or Jack looks at Mary at time t. And this has a certain degree of universality because predicates with higher arity can be reduced to binary predicates, i.e. triples. And we can introduce a variable y, and y SPOT is 1 if the statement is true at time t, and it's 0 if it's not true at time t. And the set of all these variables, or the vector or the set, is the state of the world at time t in this type of world description. In a temporal knowledge graph, so you can turn this into a graph description. The entities become nodes, and a link from entity S to entity O exists if at that time SPOT is true at time t. Most of the time we're working with static knowledge graphs, just KGs. And for people who have never seen one, here's one on the right side. So Albert Einstein is a physicist, he's a researcher. Albert Einstein is born in Ulm. Ulm is a city, Ulm is in Germany, Germany is a state. A physicist is a researcher, and so on. So it's very simple, and that's really a huge asset because it's a bridge between different communities. Because this is a structure a lot of people can address and work with, and in particular machine learning people can. So, and the technical, or not the technical, but the application breakthrough was really the Google Knowledge Graph, because they showed that this can made to work. Now, the concepts were all there, but it was not really convincingly demonstrated that it scales and it can be useful. And Google has made it scalable, so now they have 100 billion facts. It's reliable, so they have really high fidelity, 99%. They've found out how to maintain it because you need to keep it up to date, otherwise it becomes useless pretty quickly. And they showed that it's useful in search, question answering, text understanding, and so on. And it's embedded in many, many Google apps. So it's a really important part of Google background. But it's a huge asset is really the simplicity. It's about facts, just data. And this, of course, made it very attractive for industry because of this type of relational data is everywhere in industry. And here on the right side, we see a little bit like how Siemens dreams about it. There's the knowledge graph here on top, which knows everything about the product, the plans, the customers, the supply chain, the problems, and so on. So it's not a magic bullet. It doesn't just solve all these problems immediately, but it's probably the strongest technology to try some of these things. And we really early on looked on how to do machine learning in knowledge graphs because we have a machine learning background. And the idea in this Rascal approach is to, so a triple has 3 indices, subject, predicate, object, so you can map it easily into a tensor, which is a matrix with 3 indices. And we put a 1 here if we know that this triple is true and everything else is 0. So it's a huge and sparse tensor. And we can factorize it and we get a matrix out. So there's one entry here for each entity. And this is the latent embedding or the latent representation of the entity. And here's the one for the object. So these 2 matrices are identical. And then we have something called a core tensor. which has one slice, so one matrix for each relation type. And if we want to predict the plausibility of a triple, we simply take the representation of the object, multiply it by the matrix of the relation type, multiply it by the representation of the subject, and we get a number out and treat this as a confidence value. And so if we have started with a 1 and it becomes a 0 in the reconstruction, we might conclude that this is a faulty triple. But more interesting, if we added a 0 and it wants to become a 1, we can maybe conclude that this is a triple which is likely to be true based on the patterns we find in the knowledge graph. And yeah, so I was trying to emphasize that our Rascal model was really, so that's the Rascal model, the first approach, the first serious approach in embedding learning in multi-relational data and knowledge graphs. But since then, there have been a lot of methods have been developed. So for the experts are disk-mold, complex, multi-way neural networks, and the Trans-E family, Holy, and of course, graph convolutional networks, graph neural networks, and graph SAGE, which are particularly strong when you only have a single relation type. And you can do many things. If you have a machine learning, then you can reconstruct triples. You can use it in context of text data, text understanding. So a lot of people like Henry Schütze in Munich is working on that. And it gives you really a lot of interesting applications. And here's a list of things we have been working on recently. So, so this is essentially like a recommendation tool where we put everything in a knowledge graph framework, and we can easily integrate side information, background information. And it turns out by doing this, we really get better performance. And this is even online. It's being used every day. So it's a nice success to be have a real solution out there. Then we're also looking at paths, so we're not just looking at embeddings, and we can combine it with LSTM and reinforcement learning, and sort of have a debate dynamic type of reasoning. So there are two agents which sort of fight against each other, and which gives you an explainable component about how to what the plausibility of a triple is. We also do rules. We know how to integrate rules into the reasoning. That's a very recent work, and we apply to drug repurposing, and it will be shown at an ICML workshop as an oral representation. Then we are also addressing the temporal dimension. We have this fourth index, is the time index, and we combine it with Hawk's processes and LSTMs to do forecasting in these interesting data sets, which look at how countries interact in time. You can combine it with vision. So here, a triple description of images. And we also see a cognitive perspective because we think this really maps into nicely into perception and episodic and semantic memory. So, and then we thought, okay, quantum machine learning might be important for scalability questions. So we developed representation learning approaches that can be mapped to quantum circuits. Essentially, we developed three approaches: the quantum circuit embedding model, or QCE, and the fully parameterized quantum circuit embedding model, the FQCE, which is the first quantum approach to learn explicit semantic entity representations and uses relational quantum gates. We just talked about it. And the quantum tensor SVD, which is a sampling approach and uses QRAM technologies. And now Yunpu will take over and explain to you the details on that part.
Thank you very much for the invitation. Thank you very much for the introduction. And I will now briefly review the classical relational learning. So it is so in this slide, you can see the Rascal model. The classical learning of the knowledge graph is basically to derive the latent representation of the subject and of subject and predicate and object to get a unique latent representation for these entities and predicates. And there are of course other tensor models and compositional models, and all of these models, the goal of these models are to derive the score function for each triple, for each semantic triple SPO. And normally we call this score function as eta function or eta SPO. And for example, here's the explicit expression for the score function of the Rascal model. And in particularly in this Rascal model, subject and object, there are vectors and predicates are metrics. So here we use R to represent the rank, and R is a very important notation we will consistently encounter later. And there are also other tensor models, for example, Tucker, which use a co-tensor W here. And normally we learn these representation models using loss functions, for example, mean square error. So now I want to motivate why we need quantum computational resources. So the first thing I noticed that there are increasing number of distinguishable entities in the knowledge graphs. So in other words, this leads to long inference time. That is why we expect that quantum algorithm can reduce the inference time. And on the other hand, we also notice that there are increasing number of complex relational patterns in knowledge graph. So in basically learning the knowledge graph is to fit the sign pattern of knowledge graphs. So the model capacity is equivalent to the number of fitted sign patterns. So our theorem provided by Maximilian Nickel in 2013, he used the example of Tucker tensor decomposition, which I showed you before. He showed that the number of side patterns can be fitted by the Tucker model really depends on the rank R. Therefore, we also like to accelerate the algorithm with respect to the rank. So I will introduce two approaches. One is learning-based approach, and the other is the sampling-based approach. And this learning-based algorithm is basically new algorithms for knowledge graphs representation learning on quantum devices. And especially, we have the contribution that variational circuit can also learn. Using variational circuit, we can learn semantically meaningful quantum representation. And a natural question is whether this quantum representation can be used in other natural language processing tasks. So the goal of this algorithm is to, first, as I mentioned before, we want to reduce the evaluation complexity of the score function, ideally to the logarithm of R, logarithm of the rank. And we also want these algorithms to be trainable and derive unique representations for entities and predicates. And on the other hand, we also want to accelerate the inference tasks. For example, given the subject and predicate, we want to accelerate the inference of what is the correct object. So the idea is to encode entities, representations as the quantum states, especially in particularly in the coefficient of the quantum states, and prepare the predicates as variational quantum circuit, and obtain the score function, the most important thing, the score function via unitary evolution of the quantum circuit. So the most ingredients we need is the variational quantum circuit, which are introduced by Fahy, Schut, and we use the notation by Maria Schut. And in this works, we use simply single qubit variational gates, which are parameterized by 3 parameters, alpha, beta, gamma, and it's basically a 2 times 2 unitary matrix. And here we actually ignore the global phase. And we also use 2 qubit variational gates, which is a conditional rotation. This notation means that we perform a rotation on the jth qubit, conditioned on the state of the ith qubit. So a quantum circuit composed of variational gates, single qubit variational gates and 2 qubit variational gates, are basically actually a linear neural networks without any activation function. And now with the knowledge of variational gates, now we can briefly sketch how we can derive the score function. The score function, again, eta SPO. So the basic idea is we first prepare the representation, encode the representation of the subject and object using a quantum circuit. And then we evolve this subject using a predicate-specific quantum circuit. So in other words, the parameters in this part, which are in this part, they are predicate-specific. And these are two main blocks we use. The first block is to prepare the quantum state SP, and the second block is used to prepare the state O. And we want to we want to derive the score function, which is the real part of the overlap of these two states, SP and O. So how we do that, I will explain later. But before, I want to emphasize what is the quantum representation, which are basically the two blocks to prepare the representation of the subject and object. So they are basically another, in the fully parameterized quantum circuit embedding model, they are basically another quantum circuit which are entities specific, which means the architecture of the quantum circuit is fixed, but for each subject or object or any other entities, they have an entity specific parameters. And the output of this circuit is actually a quantum representation. For example, here we use a 6-qubit, and the quantum representation is just the coefficient of the resulting states, which is actually is 64 numbers. And we also need to make sure that the circuit is low enough. The depth of the circuit is low enough so that it is such a centric model. So to read out the score function epsilon SPO, we actually use a switch test such that the score function is encoded in the statics, especially Bernoulli statistics of the ancilla qubit, and so we can derive the exact relation, which is by measuring the ancilla qubit in the state of 0, and it's actually 1/2 plus 1/2 times the score function. So by measuring the statics of the ancilla qubit, we can derive the score function. And in particular, the computational complexity of this score function for each given SPO semantic triple, and is log R over the epsilon square, which is the accuracy for measuring the ancilla qubit. And to train the model, recall that all the parameters are actually in the score function, or in other words, these are parameters in the circuit for each entities and predicates. So if to learn these parameters, we use mean square error and derive the by gradient updates. And the gradients actually can also be measured by using the same circuit architecture, but using a unitary linear computation technique introduced by Schwartz in 2018. And I want to emphasize that actually the complexity of one epoch training is very huge in this case, because it depends on the training data set, the number of semantic triples we can see in the training data set, and also depends on the number of entities, and also the number of the predicates, which are NE and NP. And also, of course, here's the computational complexity for evaluating one score function. So it's actually a very huge complexity. And we simulate this on GPU and perform experiments on 4 data sets. They are very benchmark data sets: kinship, WN18, and Freebase, and GDLT. So they are very standard data sets. And to simulate that, we use 6-qubit circuits for all data sets and compare very standard metrics, for example, min rank and hits n. and we can observe very comparable results, and also sometimes we get state-of-the-art results. And similarly, recall that variational quantum circuit is very similar to neural network without any activation function. So we thought whether there are regularization techniques that could be used to improve the generalization. So the regularization, of course, should preserve the unitarity, and also it should be very simple to implement. So L2 is not a good idea, and dropout is not a good idea. In fact, we found that by applying noise, a Gaussian noise to the gate parameters for both training and test, that is different from normal regularization technique in neural network. We found that the generalization ability is improved, especially for the mean rank. You can see the low is better, and for the Higgs metrics, high is better. We all observe improved generalization ability. And also we visualized the quantum representation using TSNE, and we see the quantum representation also show similar semantic clustering effect. For example, we used TSNE, we plot the clustering of the entities from the freebase, and there are actually 15 categories in the freebase 15. And we can see here, for example, here's an example. We can see the representation of all TV series are clustered. So in other words, the quantum representation also have very good semantic clustering effect. So another acceleration, as I mentioned, the goal is to accelerate the inference. The motivation is that for each classical models, given the inference SP, subject and predicate, to infer the object, it requires actually the NE, which is the number of entities, times the polyrhythm of the R, which is the rank. This is because you need to evaluate each score functions of all the candidate entities. So we thought whether there are some alternative quantum algorithms which can accelerate this inference task, especially with respect to the number of entity and E here. So we got the idea is to prepare the quantum states using another additional index register here, and here's the ancilla qubit, and also these qubits are also for quantum representations that we have I have mentioned before, but the additional things, the index qubits. So we use these index qubits to load the representation of all entities conditioned on the ancilla qubit being on the state of 0, and load the SP state conditioned on the state on ancilla qubits being on the state 1. And similarly, we perform the Hadamard gate on the ancilla qubit. In fact, we can derive that the probability of measuring the index qubit on I conditioned on the ancilla qubit on 0 is actually also related to the score function eta SPEI. But the take-home message is that if the model is idealistic, in other words, for all the correct triples, this eta SPEI equals 1, and for all the wrong triples, this score function to -1, we can realize a quadratic acceleration with respect to the number of entity. However, that is only a heuristic or idealistic situation because this eta SPEI is never perfect, because this is a trainable method, it's a learning method. So we can never realize, never achieve this goal. So briefly, a brief summarize that quantum representations are powerful as classical representations. And in the future, we plan to simulate this on larger scale and test on NISC, and maybe on using nonlinear activation function, and also apply to other natural language processing tasks. But however, we also need to remember the disadvantage of using this learning-based method is that the acceleration with respect to the number of entities is only theoretically reachable. And the complexity of this training model is very high, especially it depends on the number of training samples, semantic triples, and also depends on the number of entity and the predicate. So that is why we are motivated to investigate another quantum algorithm, which is a sampling-based quantum algorithm using quantum tensor singular value decomposition. So this algorithm or this idea is actually extension of the quantum algorithm for recommendation system. It is a quantum algorithm which accelerates the item recommendation. So this algorithm simply assumes that the preference matrix in the recommendation system, which is a matrix of dimension m times n, has a low rank approximation, rank k approximation, and there are quantum algorithm can realize an exponential acceleration with respect to the dimension of this preference matrix. So the question is how we can generalize to knowledge graph. There are several difficulties. For example, recall that the knowledge graphs tensorized data, especially it's a three-way tensor, and also we need to at least intuitively prove that tensor or the semantic tensor from the knowledge graph also have a low rank approximation, and for some quantum subroutines, they simply ignore the sign of singular values. So next, I will introduce, before introducing the quantum algorithm, I will briefly introduce what is the tensor SVD. So for an arbitrary tensor, n-way tensor with dimension d1 times d2 times dn, if this tensor A can be written as a sum of R rank 1 outer product, so with singular values sigma 1 to sigma R, and these eigenvectors are orthogonal. So then we say that the tensor A has a tensor singular value decomposition with rank R. And also we also need to I also want to introduce the specification of A, of this tensor A, because normally we cannot observe all the elements of the A. So we assume that the tensor A is randomly subsampled with probability P, and the P is called subsampling rate. This P is called subsampling rate. And normally for this quantum algorithm or for classic simulation, we also need a rescaling step, which means the advantage of this rescaling step is that the expectation value of subsampled and rescaled tensor exactly equals the unsubsampled and unrescaled tensor.
Just a quick remark. 2 minutes you would still have, and then the discussion time would start. So just to give you a hint. Okay.
Yes. And we can write the original tensor as a subsampled tensor with noise tensor. And we derive several theorems to show that the low rank approximation of this subsampled tensor can be, for example, we derive two theorems. We show that the low rank approximation of the subsampled tensor can reconstruct the original tensor A, such that the query, the inference on the knowledge graph can be realized. And especially we mentioned there are two very important criterions. First, the original tensor A should also be well approximated by a low rank tensor SVD called AR. And also especially the most important criterion is that the subsample probability P has to larger than some quantities. And I also need to emphasize the theorem, the first classical theorem cannot be directly applied to quantum, which means there are no quantum counterpart for it, because for the tensor case, the singular values of this tensor SVD may be negative. And therefore, I derived the second theorem by introducing another projection scheme, which is called absolute singular value projection with predefined threshold. The notation indicates that I want to project the tensor to the eigenvalues whose absolute value is larger than a predefined threshold. Similarly, we can also show that this tensor, this reconstruction error is also bounded, and which is good. With bounded reconstruction error, we can the inference on the Hodge graph is guaranteed. And also, of course, there's another very crucial condition is that the subsample probability must larger than much larger than several quantities, and that is very that's actually very can be intuitively understand that if the subsampling rate is very small, of course the original tensor cannot be reconstructed, and then your inference can also not be realized. So the quantum algorithm, a short message is can realize exponential acceleration by sampling, and we need a QRAM to prepare the quantum state, whose coefficients are the subsampled and rescaled the semantic tensor, and also we need a quantum tensor contraction. And the rest of the algorithm is very standard, using quantum PCA, quantum phase estimation, and quantum singular value projection. But the most important part is actually here. This part of quantum state actually correspond to the tensor singular value projection with predefined threshold tau. And of course, we cannot simulate this quantum algorithm, so we simulate the classical algorithm, and using the classical SVD and the similar loss function, and with a penalty to encourage that the embedding metrics are orthogonal and normalized. And we can also observe also some state-of-the-art result and comparable result on standard data sets. And one thing I want to emphasize, the sampling rate and rescaling, and especially the rescaling plays a very important role. And now we come to conclusion that quantum representation can heuristically realize the quadratic acceleration for Hodge graph inference, and they are very powerful, have comparable results with the classical method, and therefore whether they can be used to other NLP task. And the other quantum algorithm is quantum tensor absolute singular value projection, realize an exponential acceleration with respect to the tensor dimension. And whether this the other question is whether this inference this can be used, this quantum algorithm can be used to other tensorized data. And here's the if you're interested, here's the other two publications. Thank you very much.
Thank you very much. Thank you very much for the talk. Are there questions from the audience to either of the two speakers, I guess? Maybe I can start, since you are, that's a more general question, since you are in a company, how do they view applications of quantum machine learning, which seem to be still far out there? So what's the view of this?
Well, I guess I should answer that. So we are exploring this space. I mean, there are certain pretty substantial activities in Germany, like I think one quantum computer will be built in the Stuttgart area, one in the Munich area. We are applying for different research projects, also pursuing these ideas we presented today and other ideas. So it's we see a long-term horizon, but we see, for example, in energy networks, there could be a closer goals we can reach in terms of optimizing energy networks. But I think it would still be it's still considered exploratory research, where, I mean, okay, one motivation is always to be prepared for the time when quantum breakthroughs are happening, and a lot of solutions maybe need to be mapped to quantum algorithms. So I don't think a company like Siemens doesn't have the one killer app or whatever, the one big application we are pursuing. I think it's currently it's in research and it's in an exploratory phase. But for example, we also have a strong, Siemens has a strong collaboration with Atos, and Atos has a quantum simulator. And we are also dealing together with these companies. So there are multiple of efforts, but not the one I can say, okay, this is our, let's say, quantum killer application we're working on.
Okay, sure, yeah, thank you. Are there other more questions from the audience? Still have a few minutes if you like.
Oh, sorry.
Yeah, there's someone, yeah.
Yeah, Florian, it's me.
Okay, good. Do you want to ask a question?
Yeah, so yeah, I'm a bit puzzled about this sparsification. So why is this? Because you get exponentially many entries in your tensor and you only have finite data? What is the reason that you need this sparsification?
I briefly mentioned what is the reason I want to rescale that, and also the subsampling. So for normal knowledge graph, actually the knowledge graph itself is already subsampled, right? Because we want to inference the unobserved entities in the knowledge graph. So which means the knowledge in the inference is basically a completion. So it's the knowledge graph on, or like, for example, inferring on test data set is also a knowledge graph completion. Actually, I want to mention here. So a comparison between what is the preference matrix completion is actually item recommendation, and semantic tensor completion is actually useful for knowledge graph inference. So the knowledge graph itself is already subsampled, but the difficulty is to estimate what is the subsample probability P here. And also another advantage of the rescaling, I mean the rescaling to derive this subsampling rate is that we can the expectation value of this A, of this subsample rescaled A is actually equals to the original tensor, and then we can use this condition and use this A, the original tensor is equals subsum tensor plus noise tensor. We can derive all these two theorems here, first and second theorems here, these two theorems by estimating the Fourier norm and spectral norm of this noise tensor. That is the purpose of rescaling. And the subsampling is that the tensor, the semantic, especially the semantic tensor is itself already subsampled. So, and also we perform experiments on how the subsampling rate can affect the result. So these are just some metrics, and we always observe that the subsampling rate is very crucial, and especially as we estimated for these two cases, the result has the best performance. The model has the best performance when the sampling rate is equals 0.9. That is also basically what we want, what we expect, because for the knowledge graph completion task, the training site is the whole data site or the original tensor is divided into training and test. Is normally not 90% are training, 10% are test data sites, which means the subsampling is 90%. So it's basically yes, it's basically only for these two data sites. But for the Yago and other data side, we guess we observe experiments. Of course, is the we observe that subsampling rate is 0.1, but of course, Yago is a very large and noisy data set, and also since it's very large, there are maybe a lot of missing links in the data set. So that's why the sampling sample rate is very small, actually.
Thank you. Thank you.
Okay, thank you.